tangents, tangent's parent function is 0, asymptote, 0, asymptote, 0. And it has half of a tangent here, a full tangent there, and half of a tangent there. And these do keep going, but that would be coterminal. These would be negative. So keep in mind that the parent function of tangent kind of looks almost half formed in the way that it looks. So you can see that I did that here. 0, asymptote, 0, asymptote, 0. And then just like with cosine and sine, I'm going to forward shift this pi over 2, and I'm going to shift this up 1. So I take this point, I phase shift it or translate it pi over 2 and then up 1, pi over 2 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 up 1. The asymptotes are kind of interesting the way you want to think about this. This asymptote is being moved forward pi over 2 and then up. So it doesn't really move, right? Same thing with this one. It's being moved forward pi over 2 and then up. So it just does the pi over 2 and not the upward movement. So I'm left with this dot here. And so that will give us our tangent graph. Our tangent graph will end up looking like this, a little bit more fully oriented once I've shifted it. And there is one over here, right? There's one over here. Those would be coterminal values. These would be the negative values, the negative rotationals. So there's our graph. The range is negative infinity to infinity, but the domain always makes kids look like, okay, how do I figure that out? You really have to talk it through. When you look at this graph, there's an asymptote here at 0. So 0 pi, there's an asymptote, right? And then there's also one here at pi, right? 1 pi. And there's another one at 2 pi. And you could understand there'd be one at 3 pi and there'd be one at negative pi. What numbers are negative 1, 0, 1, 2, 3? A lot of people will say integer. You could call those natural numbers. So it's sort of up to you how you describe this. And this is probably the most routine way, is x such that x is a real number, but x is not equal to integer pi values. Some teachers will say x such that x is a real number where x is in, meaning any pi value where n is an integer. But this is kind of a combination of those two things. It's a little shorter. All right, so let's go over some of the vocabulary. There is no amplitude. So we go back to the vertical dilation concept that amplitude is based on from Algebra 2. You can see how the Algebra 2 review is so important here. So all of a sudden now we don't have an amplitude, we have a vertical dilation. You don't see one, there isn't one right here. My period, remember the period is for tangent is pi over b, right? It's pi over b, which in this case would be pi over 1 here, okay? The phase shift is right pi over 4. You saw that clear there, and the vertical shift is up 1. All right, let's take a look at our last tangent value, and then I'll show you some calculator things that will help you keep all this straight. So the tangent here, you can see that I've given you one that is a requires a factor out of a GCF. So you're going to take out this 2, make a parentheses, this x, and this is the part we got to be really careful about. When I divide 2 by here, I get 1, but when I divide 2 by pi, I get pi over 2. Which is going to shift the graph backwards. But first, because of the order of operations, I have to take care of this right here first. So normal tangent graph, 0, asymptote, 0, asymptote, 0, little half-made thing here, full thing there, half thing there. So you can see that 0, asymptote, 0, asymptote, 0. And now we're going to divide all of the key parent function points by 2. So 0 divided by 2, 0. Pi over 2 divided by 0 is pi over 4. Okay, the next one will be at pi divided by 2 is now at, pi over 2 divided by 2 is now pi over 2. 3 pi over 2 divided by 2 is now 3 pi over 4. And 2 pi divided by 2 is now pi. So you got a lot going on there, but what's happened is everything has shrunk down into here, creating a compression horizontally, right? And so you have your little half tangent there, you have your full graph there, and half of it there. It would keep going, but you can see that this graph is represented here, but what has happened is we have compressed it, and that changes the period to be half of what it would be normally. And that would be it, but I also have to phase shift the graph pi over 2. And this is interesting. Remember earlier in the notes I said that if you phase shift a graph equal to its period, you'll actually get the same graph back. So if I look at this graph right here, when I phase shift this graph back pi over 2, what ends up happening is this graph, this asymptote right here is going to shift over to there, but this asymptote is now going to shift right on top of that asymptote, and that 0 is going to shift right on top of that 0. So by doing this phase shift, I actually phase shift the graph right back onto itself, and that goes back to what I was talking about earlier in the notes. Again, just a quick review of tangent, because it does throw people for a little bit of a loop. The period is pi over b instead of 2 pi over b, and this happens for sine and cosine, but I did this with the tangent one. If you phase shift a trig function equal to its period, the graph appears not to change, and you can see that here in example 6. Okay, and don't forget that we would also have some more asymptotes here, and there'd be another graph going through here, and then another asymptote. It just keeps going. That's really important when we talk about the domain. This keeps going. My range, of course, would be negative infinity to infinity, but my domain is occurring, as you can see, at 1/4, 3/4, 5/4, 7/4, and then it would be 9/4 or negative 1/4 pi. And so what's happening here is the domain is occurring at all real numbers except x cannot equal odd. This says odd in math language, pi over 4. And I think most kids understand if they just say it doesn't happen at odd pi over 4, so they can see it's odd numbers of pi over 4. So the way I got this, again, just to show you that algorithm, is that I took the odd numbers, 1, 3, 5, 7. I called this A1. The common difference, and this is a review from sequences in series in Algebra 2, is 2. So I plug those in, A1's 1. I distribute the common difference, I combine like terms, and I get this equation. So in sequences of series, we would write it like that, but in describing domains, we write it more traditionally with the number first, 2n minus 1, as opposed to negative 1 plus 2n. All right, so let's take a look at how we would also, maybe check some of this on our calculator, a little review of some calculator features as well. There's a lot of review when you get to this level in math, and it's important to know where all this stuff comes from. So let's take a look at the first one we looked at, which was sine x minus pi over 2 plus 1 in the calculator. First thing you have to understand is that there is a pi, and so with the pi, I want to make sure my mode is on radian. If this was degrees, if this were minus 90 degrees, I would use degree mode. Very uncommon with graphing, though. We typically graph in radian mode. So you want to make sure it's in radian mode. Then we're going to type it in, okay? And then there's actually a special menu to graph on a TI calculator or a Casio, even on Desmos. If you go to Windows, and you go to Zoom, and you go to Trig is right here. It's choice 7. You can either hit 7 or scroll down to it. But this gives a graph that has all 4 quadrants, which is very disorienting because it makes you think of the unit circle in the wrong way. The unit circle actually starts here at the y-axis. So we're going to go back into our window, and we're going to change this to 0, and we're going to go to 2 pi, so it looks just like the unit circle we do. This tick mark right here is pi over 2, which is very helpful because that's where our parent function 5 values that we have to know go. Okay, remember the 5 values of 0, 0, 0 max, 0 min, 0. They occur at pi over 2 values. My graph paper goes from negative 2.5 to 2.5, so I'm going to put that in. And then when I hit graph, you're going to see a graph that looks exactly like what we drew on our graph paper. Mine's just in black. And obviously the calculator's is a little bit nicer. All right, so let's take a look at the next one. So when we look at the next one, we can look at this graph. This one will have a nice compression on the sine value here. So if I go to y equals and I type in sine of 2x minus pi, the original problem we had, okay, and I graph that, you will see that it looks just like what we have here. Okay, we can even do a cosine one, no problem. We can do a cosine one as well. So when I look at the cosine one, here we go. I have negative 2 cosine of 1/2 x. Okay, I graph that. As you can see, it looks just like what we have, but mine's red and theirs black. So let's take a look at that tangent one. It's a little more interesting, the one that overlapped itself. And we'll type it in both ways so you can see it overlapping on the calculator. If I go here and I type in tangent of, tangent of 2x plus pi, and then I hit enter, and I graph the same thing, but I'm actually just going to get rid of that. Remember, if I phase shift the same amount that I have a period, I get the same graph. So tangent of 2x, okay, the first one will be black, the second one will be blue, and you'll see it graph right over top of itself. Black one, blue one. I hope you liked this video. I hope it helped you understand how to graph. I hope it went over some good vocabulary for you, and I hope you have a good time learning how to graph trigonometric functions.